I've been waiting to do this video for a while because my electric shaver broke and I needed a new one. So now I've got a new one. So now I'm doing a video on the barber's paradox. So I've been doing a lot of paradoxes in this series. The barber's paradox is kind of an interesting one. It's a sort of informal statement of a formal paradox that's quite important in the history of these sorts of ideas. Now, the barber's paradox essentially goes that does the barber who shaves everybody who don't shave themselves shave himself? And of course that's a paradox, because if that barber shaves himself, then he doesn't shave himself, because he only shaves people who don't shave themselves. But if he does shave himself, well, if he does shave himself, then he doesn't, and if he doesn't, then he doesn't. So that's kind of a fun little paradox. But where it comes from really is from set theory. And I mentioned in the previous video, I spoke a little bit about Venn diagrams and the whole idea that maybe instead of thinking of propositions having assigned values, true or false assigned values, it might be better to think of cutting the world up into segments, where in one part of the world the statement is true, and in another part that statement is false. So that's a sort of a slightly more inclusive way of thinking of how truth works, in a sense. And one of the reasons this sort of became a way of looking at it, sort of emerging out from classical logic, is because there was a movement to try and develop a formalization of mathematics, to put mathematics on a logical basis. Now, most people intuitively think of mathematics as being logical, but as we've seen, logic has a very strict definition, and when we apply that strict definition, it very quickly becomes clear that the relationship of mathematics to strict logic is complicated. And I'll just give an example of where that sort of complication comes in. If you think of a puddle of water, I take one puddle of water and I add another puddle of water, and I put them together. Do I get two puddles of water? No. So in other words, in logic, we would expect that kind of thing to hold. But in mathematics, it doesn't hold, because one is a statement of some sort of set of affairs. So 1 + 1 = 2 only for those sort of sets of affairs where 1 + 1 = 2. So that's not great. we need something for logic. We need something to consistently hold throughout, as we saw with the ex falso quadlibet, that when you have contradictions coming out of things, those contradictions feed through everything. So it's not good enough to just say, oh well, in this case or in that case or in that case. Everything needs to work consistently. So there was a kind of a desire to find a way to put mathematics on that sort of footing, and essentially one of the ways that it was thought to do that is to think of sets. So to establish mathematics from the ground up. Of course, early mathematics was kind of used for counting sheep, or for finding straight lines, when you're building pyramids or whatever, and those sort of practical applications. And it was clear that this wasn't going to work consistently in that way that was needed. So it was thought, well, maybe using sets as the basic principle would kind of give that leverage, that's a sort of I don't want to say more rational, but a way in to setting logic, to setting mathematics on that logical footing. So if one thinks of it this way, when we use the conjunction, when we use and, we're talking about the union of sets. We're talking about the disjunction, we're talking about if we're talking about the disjunction of sets. We do. So basically, you can think of truth statements about the world as relating to statements of way of cutting the world in that sort of way. So one can think of, if you say that the statement 1 + 1 = 2 is true for all of those things that fall into the region of things for which 1 + 1 = 2, and it's false for all those other things. So now we got these two regions of sorts of things. One of these regions where everything is false, where that statement is false of all of those things, and this other region where the statement is true for all of those things. So I mean, I'm not really going to go into the formalities of all this. This isn't really the purpose of this video series. The main purpose again is just to discover why essentially we need to take care with proof statements and evidence, and of course eventually I want to bring that back to music, but the basic point is that there was this idea that we could use sets like that to establish a formal basis for mathematics. And getting back to where we started with the Barber paradox, essentially the original statement of that is actually that the set of all sets that doesn't contain itself, the set of all sets that don't contain themselves, is the sort of the formal example of that paradox. Because if a set doesn't contain itself, it is in that set, and if it does contain itself, it isn't in that set. So it's paradoxical. So here you have something that is both true and false at the same time. And of course, I mean, this sort of thing of using contradictions like that to sort of like prove a whole chain of things. There's a long history in mathematics, the whole idea of proof by absurdity. So you assume one thing to be true, and you prove a contradiction, and then that thing that you assume to be true can't be true then, because it leads to a contradiction. So that whole ad absurdum argument means that basing our idea of mathematical logic on sets kind of essentially falls apart, and that was called naive set theory. So this is now specifically talking about naive set theory in the 19th century, coming from that whole idea of Frege had the Begriffsschrift. If I'm pronouncing that correctly, my German is not so great. But essentially the concept piece or something like that. But yeah, that the whole idea was to set mathematics on the basis of set theory for that reason. And the Barber's paradox, which is just a restatement of Russell's paradox, essentially showed that using sets as a fundamental fundamental basis for mathematics leads to this paradox, and that essentially scuppers that whole project. So what followed, and why this is important, is because there was sort of a general push and an effort made then to say, well, okay, if it's not naive set theory, how can we modify this? And maybe can we find some other way of dealing with things that either solves this problem or makes it go away, so that we can establish mathematics on some sound footing? Because it was believed at the time that mathematics essentially could be made to be equivalent to logic. And one of the big social problems that I believe we're facing, and maybe this is more the sort of purpose of the series, one of the big social problems that I believe we're facing right now is that this concept is still with us. There still isn't a general public acceptance of the idea that mathematics cannot be reduced to logic, fundamentally. And And so that's as well. I'll just spend a couple more videos just looking into this whole thing of some other alternative approaches to trying to solve this, because as I say, intuitively it should work. Mathematics seems pretty logical. So yes, I think that's enough for tonight, but that's the basic idea. Great. Bye.